All right, I think we're good. So here's the here's the plan. It's never good when somebody starts laughing when they're describing the plan. It's sinister. Okay, so what we have is a pinball plunger, pulling the plunger back. He's about to let go. Send this pinball up the ramp so that it barely goes into play. So we want the pinball to just roll up to the edge of the ramp and just begin. So what I'm going to do here is I'm going to say the velocity of the pinball at this point, in order to pass this point and not stop, has to be 1.00 centimeters per second. Okay? So the velocity of the pinball as it rolls up here has to be 1 centimeter per second. So it's just rolling. And then it becomes in play at this point. Now, the length of the pinball ramp is on the base of the ramp is 2 meters, 2.0. Let me make that 3 significant figures. 2.00 meters, hint there, and 15.0 centimeters tall. So this distance that you're going to have to calculate using a little Pythagorean theorem probably needs to be 3 significant figures. 3 sig figs, 3 sig figs, 3 sig figs. Okay, so the mass of the pinball is 75 grams. I don't even know if that's right. Let's make that 105 grams. Okay, so mass of the pinball is 105 grams. The coefficient of kinetic friction between the ball and the ramp is 0.08. Let's go 0.0800. That way we have 3 sig figs throughout. 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs, 3, all the way across. So the question is, if this is pulled back 15.0 centimeters, so the stretch is 15 centimeters, what is the K value of the spring for this to all work? So that the pinball is launched, it rolls up the ramp, and it's barely in play at this point, meaning the velocity is 1 centimeter per second. Okay? Big hint is to use the coefficient of friction to figure out the friction force, and then use conservation of energy. So figure out what your elastic potential energy has to be equal to here to overcome the work. Hint, work. And then all of the energy at the end has to equal. Okay? Good luck.